Have you ever looked up at the night sky and felt that tug of curiosity, wondering what secrets the stars might be hiding? We all learn the basics in school: the planets, the moon phases, maybe even a little about black holes. But what if I told you that everything we were taught barely scratches the surface? Space, as it turns out, is holding onto mysteries so strange, so breathtaking, that they've been kept out of the classroom for far too long. Today, we're going on a journey beyond the textbook, into the heart of the cosmos, to uncover 30 astonishing space facts that will make you rethink everything you thought you knew. Just imagine there are worlds where it rains diamonds, stars that sing, and corners of the universe where the laws of physics as we understand them simply don't apply. These aren't science fiction ideas, they're real, evidence-backed wonders happening light years away, and yet most of us have never even heard of them. This video is your ticket to that adventure. We'll explore cosmic phenomena that defy imagination, from silent explosions in the vacuum of space to the eerie music of celestial bodies, and even the possibility of ancient oceans on distant moons. Each fact is a reminder of how vast, strange, and beautifully unpredictable our universe truly is, and how much there still is to discover. So settle in, open your mind, and get ready to see space in a whole new light. Trust me, by the time we're done, you'll never look up at the night sky the same way again. Let's start with a fact that hits remarkably close to home, quite literally happening right above our heads. Our own moon is in the process of slowly leaving us. Every single year, the moon drifts about 3.8 centimeters farther away from Earth. That's roughly the same rate at which your fingernails grow. Now, that might not sound like much, but over the immense timescales of our solar system, this tiny annual migration adds up to a dramatic story. This entire process is driven by the gravitational tug of war between Earth and the Moon, a dance powered by tides. The Moon's gravity pulls on our planet, most noticeably on our oceans, creating the bulges of water we know as high tides. But here's the fascinating part. Earth rotates on its axis much faster than the Moon orbits around us. This means our planet is actually spinning ahead of that tidal bulge. The gravitational pull from that slightly ahead bulge acts like a constant, gentle tug on the Moon, giving it a tiny bit of extra energy. This energy pushes the Moon into a slightly higher orbit, moving it further away each year. The implications of this gradual departure are profound and will reshape our world in the far, far future. First, consider eclipses. Total solar eclipses, that breathtaking moment when the Moon perfectly covers the Sun, are a beautiful cosmic coincidence. The Sun is about 400 times wider than the Moon, but it's also almost exactly 400 times farther away. This is why their apparent size in our sky matches so perfectly. As the Moon continues to retreat, its apparent size will slowly shrink. Hundreds of millions of years from now, it will appear too small to completely cover the Sun. The era of total solar eclipses will eventually come to an end, leaving only partial and annular ring of fire eclipses for any future inhabitants of Earth to see. This changing distance will also fundamentally alter the rhythms of our planet. The Moon's gravitational influence stabilizes Earth's axial tilt, which gives us our relatively predictable seasons. A more distant moon would mean this stabilization effect weakens, potentially leading to much more chaotic and extreme climate variations over long periods. Furthermore, the transfer of energy that pushes the Moon away also acts as a brake on Earth's rotation. This means our days are getting longer imperceptibly by about 1.7 milliseconds per century. Billions of years ago, a day on Earth was only 18 hours long, and the Moon loomed much larger and closer in the sky. In another billions of years, a day will be significantly longer than 24 hours, and our familiar Moon will be a noticeably smaller companion. It's a silent, slow-motion farewell happening right before our eyes, a testament to the dynamic and ever-changing nature of even our most familiar celestial relationships. While our own moon is slowly drifting away, another world exists out there that is almost too luxurious to be real. Imagine an entire planet where a significant portion of its mass isn't rock or iron but diamond. This isn't science fiction. It's the best scientific explanation for a fascinating exoplanet known as 55 Cancri e, located a mere 40 light-years away in the constellation Cancer. This super-Earth, about twice the size of our own planet but with 8 times its mass, orbits its sun-like star so closely that a single year there lasts only 18 hours. Surface temperatures are believed to soar to a searing 4,200 degrees Fahrenheit, hot enough to melt most metals and create a world that is likely a scorching, hostile landscape. But the true wonder of 55 Cancri e lies beneath this infernal surface. Astronomers believe the planet's composition is incredibly carbon-rich. Here on Earth, with a richer oxygen content, carbon forms common rocks and minerals. But under the immense pressure and heat within a massive planet like this, carbon undergoes a spectacular transformation. The crushing weight of the planet's own mass, combined with the extreme internal heat, forces carbon atoms to crystallize into a lattice structure, creating a vast mantle of diamond that could be hundreds of miles thick, potentially surrounding a core of solid carbon. Attempting to put a price tag on such a world is a fun but ultimately futile exercise. If we could somehow mine and retrieve this cosmic treasure, its value would be so astronomically high, estimated to be around $26 nonillion. That's a 26 followed by 30 zeros, that it would instantly shatter any concept of Earth's economy. The very act of bringing such a quantity of diamond to market would make the gemstone utterly worthless due to sheer oversupply. Its true value isn't in potential wealth, but in what it teaches us about the incredible diversity of planetary formation. 55 Cancri e stands as a glittering testament to the fact that the universe can craft worlds far stranger and more magnificent than anything we could have dreamed up in a classroom. If you think the weather on Earth can be unpredictable, wait until you hear about the hurricane-force chaos raging on our sister planet, Venus. While it may look like a serene, cloudy jewel from afar, Venus is home to one of the most violent and baffling weather systems in our entire solar system. Its upper atmosphere is dominated by supersonic winds that scream around the planet at speeds up to 720 kilometers per hour. To put that into perspective, that's more than twice the wind speed of the most powerful Category 5 hurricane ever recorded on Earth. These winds are so incredibly fast that they complete a full lap around the planet in just 4 Earth days, a phenomenon known as superrotation because the atmosphere is literally spinning around the planet 60 times faster than Venus itself rotates. This creates a truly surreal situation. A single day on Venus, the time it takes to complete one full rotation, lasts longer than an entire Venusian year. So if you were somehow floating in those upper cloud decks, you would experience the sun rising and setting only once every 243 Earth days, but you would be whipped around the entire planet by the wind once every 4 days. The driving force behind this perpetual, planet-encircling hurricane remains one of the great unsolved mysteries in planetary science. Unlike Earth, where our weather is powered primarily by solar heating and the planet's rotation, Venus rotates incredibly slowly, so that can't be the engine. The leading theory suggests that the tremendous heat from the sun on the planet's day side creates massive pressure differences, and the transfer of heat from the equator to the poles through giant atmospheric waves provides a constant push, accelerating the gases to such incredible speeds. It's a complex thermal engine operating on a global scale, a constant tempest fueled by the sun's immense energy. Visualizing this from space, you wouldn't see a calm, uniform blanket of clouds. Advanced satellite imagery reveals a dynamic, violent atmosphere. The clouds themselves are not made of water vapor but of corrosive sulfuric acid, swirling in vast hurricane-like patterns. Dark, ominous vortexes spin at the poles, and the entire cloud deck is pulled into long, streaky bands that streak across the planet, clearly showing the direction of those supersonic winds. It's a world of relentless, savage weather, a permanent storm shrouding a scorching surface, proving that even our closest planetary neighbors can be utterly alien and hostile. While Venus rages with atmospheric fury, the planet Mercury presents us with a very different kind of drama, a slow, silent, and planetary-scale collapse. For a long time, we considered Mercury to be a static, geologically dead world, a heavily cratered relic from the solar system's violent beginnings. But it turns out this small, sun-scorched planet is still very much active, and it's actually shrinking. Yes, the entire planet is contracting, getting smaller over billions of years. The reason for this lies deep within Mercury's core. Despite being the smallest planet, Mercury is incredibly dense, meaning it has a massive iron core that makes up a huge portion of its interior. This core has been steadily cooling down ever since the planet formed. Just like a baked apple wrinkles as it cools and loses moisture, a planet's surface wrinkles and contracts as its hot interior cools down and solidifies. On Mercury, this global shrinkage has created breathtaking geological features called lobate scarps. These are not mere cracks or simple cliffs. They are colossal thrust faults, essentially giant wrinkles in the planet's crust that can be hundreds of miles long and over a mile high. Imagine a cliff face taller than the Grand Canyon snaking across the landscape for a distance longer than your entire home country. Our most detailed evidence for this ongoing process comes from NASA, a messenger mission which orbited Mercury from 2011 to 2015. The spacecraft's incredibly detailed imagery didn't just confirm the existence of these scarps. It revealed something astonishing: small, fresh-looking scarps cutting right through ancient impact craters. This was the smoking gun. If the planet had stopped shrinking billions of years ago, all such scarps would be old and heavily cratered themselves. The fact that we see young, pristine scarps means the contraction is geologically recent and is almost certainly still happening today, subtly reshaping the planet's surface even now. This discovery completely rewrites our understanding of not just Mercury, but of terrestrial planets as a whole. We used to think that small planets with their high surface area to volume ratio would lose their internal heat very quickly and become geologically inactive. Mercury, the smallest of all, is proving that assumption wrong. Its continued cooling and contraction demonstrate that planetary evolution is a billion-year process that doesn't simply stop. It tells us that even the most seemingly inert worlds can harbor dynamic, ongoing change, reminding us that in our solar system there is truly no such thing as a dead planet. For centuries, Jupiter's Great Red Spot has been the solar system's most iconic storm. A colossal swirling vortex so vast that it could easily swallow our entire planet whole. This massive anticyclone, a high-pressure storm raging in Jupiter's southern hemisphere, has been observed for at least 190 years, and some estimates suggest it might have been churning for over 350. It's been a permanent fixture, a storm that could outlast civilizations, but recent observations have revealed something startling. This seemingly eternal tempest is undergoing profound changes, shrinking and transforming before our very eyes. Data collected over the past several decades shows the Great Red Spot is not what it once was. In the late 19th century, it was estimated to be over 40,000 kilometers wide enough to fit 3 Earths placed side by side with room to spare. Today, that measurement has dwindled to approximately 16,000 kilometers. While it's still large enough to contain our planet, the rate of this shrinkage is accelerating, and the storm itself is becoming more circular in shape rather than its classic oval. Along with its physical contraction, the spot's famous crimson hue has also been fluctuating, at times fading to a pale salmon pink before darkening again to a more intense brick red. The exact chemistry behind its color remains one of Jupiter's great mysteries, with theories suggesting complex compounds like ammonium hydrosulfide or organic molecules known as tholins being churned up from deeper within the atmosphere and altered by solar ultraviolet radiation. Our most intimate glimpse into the heart of this transformation comes from NASA's Juno spacecraft, which has been orbiting Jupiter since 2016. Juno's suite of instruments has peered deep beneath the cloud tops, revealing that the Great Red Spot is not a shallow surface feature, but is incredibly deep, plunging anywhere from 300 to 500 kilometers down into the planet's atmosphere. This is astounding. It means the storm's roots extend dozens of times deeper than the deepest ocean on Earth. This new data suggests the storm might not be dying in the way we might think. Instead of simply dissipating, it could be in a process of transformation, perhaps being stretched and sheared apart by powerful jet streams that dominate Jupiter's atmosphere. The ultimate fate of this legendary storm is a topic of intense debate among planetary scientists. Some models suggest the shrinkage could continue until the Great Red Spot eventually fragments and vanishes entirely within our lifetimes. Other theories propose it might stabilize at a smaller size or even merge with other, smaller vortices to form a new kind of storm system. Its potential disappearance would mark the end of a celestial era, the fading of a landmark that has defined our view of Jupiter since the first telescopes were pointed skyward. Yet, even as we watch this giant waver, its ongoing transformation offers an unprecedented opportunity to understand the dynamic and turbulent atmospheres of gas giants, not just in our own solar system, but on the countless exoplanets we are discovering around other stars. The Great Red Spot story is a powerful reminder that in the cosmos, even the most permanent-looking features are part of an endless cycle of change. Just when we thought we had Pluto neatly categorized as a distant, frozen relic, this dwarf planet sent a curveball that shattered expectations. The New Horizons flyby in 2015 revealed a world of staggering geological complexity, and one of its most jaw-dropping features was the apparent presence of ice volcanoes, or as scientists call them, cryovolcanoes. These aren't your typical fire-breathing mountains. Instead of spewing molten rock and ash, cryovolcanoes erupt with a slushy, viscous mixture of water ice, ammonia, methane, or nitrogen. Think of it not as lava, but as a kind of antifreeze slurry oozing slowly onto the surface. On Pluto, the evidence points to two massive candidates, Right Mons and Pickard Mons, which are unlike any geological features seen elsewhere in the solar system. Right Mons stands nearly 4 kilometers high and stretches over 150 kilometers across, making it a behemoth on the planetary scale. Instead of a single classic volcanic peak, these structures appear as gigantic mounds with deep central depressions, more like collapsed blisters or welts on Pluto's frozen crust than the conical volcanoes we know on Earth. The existence of these cryovolcanoes is a monumental clue, pointing directly to a startling truth about Pluto's interior. It must be far warmer and more dynamic than anyone ever predicted. For this slushy mix to remain liquid enough to erupt, it requires a heat source powerful enough to melt its way through an icy shell that is likely more than 150 kilometers thick. The primary suspect for this internal warmth is the slow, lingering decay of radioactive elements left over from Pluto's formation over 4 billion years ago, trapped within its rocky core. This heat, however minimal, seems to be just enough to maintain pockets of liquid water, or at least a malleable icy slush deep beneath the surface. This revelation opens up the most thrilling possibility of all. Pluto could harbor a subsurface ocean, a layer of liquid water kept from freezing by the antifreeze-like properties of dissolved ammonia, and the insulation provided by the thick, overlying ice shell might exist to this very day. The mechanism for the eruptions themselves is thought to be similar to that on Earth, just with different materials. pressure builds from below as this warm slush rises, eventually finding a weakness in the overlying ice. It then pushes through, not with a violent explosion, but with a slow, oozing flow that freezes solid upon contact with Pluto's incredibly cold surface, gradually building up those massive, distinctive mounds over immense periods of time. Finding active geology and potential ingredients for life on a world 6 billion kilometers from the Sun forces a complete rewrite of the textbooks. It proves that even small, distant bodies once written off as inert and frozen can hide warm, potentially habitable interiors. Pluto is no longer just a frozen rock at the edge of our solar system. It is a living geological world, whispering tantalizing secrets about the hidden oceans that might be waiting in the dark, cold reaches of space. Yet for all their breathtaking grandeur, Saturn's iconic rings hold a secret that completely upends our understanding of the solar system's history. We once assumed these magnificent structures were as ancient as Saturn itself, forming alongside the planet over 4.5 billion years ago. But astonishing evidence now tells a different story. Saturn's rings are a surprisingly recent addition, a fleeting celestial spectacle that appeared long after the dinosaurs first walked the Earth and may vanish long before our Sun dies. The most compelling clues to their youth come from the data collected during the final, daring orbits of NASA Cassini mission. As the spacecraft prepared for its grand finale, it flew between the planet and its rings 22 times. By carefully measuring how the probe's velocity was minutely affected by the gravitational tug of the rings, scientists were able to calculate their total mass with incredible precision. The result was shockingly low. While they span nearly 300,000 kilometers in diameter, the main rings are incredibly thin, often no thicker than a two-story building, and are composed of nearly pure water ice. Their total mass is only about half that of Saturn's icy moon Mimas. This minuscule mass was the first major clue. If the rings were truly billions of years old, they should have been darkened and polluted by a constant rain of micrometeoroid dust from the solar system. Their pristine, bright ice suggests they haven't been around long enough to accumulate significant debris. Further evidence comes from the ring's composition itself. Using its onboard instruments, Cassini was able to analyze the contamination levels within the ring particles. The data showed the pollution was far too light for a 4.5 billion-year-old structure. By calculating the known rate of cosmic dust accumulation, scientists could essentially work backwards, determining the rings are likely only between 100 and 200 million years old. This places their birth squarely in the Cretaceous period on Earth, a time when Triceratops and Tyrannosaurus rex roamed the continents. Imagine that while giant reptiles dominated our world, a catastrophic event was unfolding near Saturn, creating the most beautiful structure in our solar system. But what event could have created such splendor so recently? The leading theory points to a dramatic and violent celestial accident. The most plausible scenario suggests that a moon, perhaps about the size of Mimas, strayed too close to Saturn in its distant past. The planet's immense tidal forces would have torn this unfortunate moon apart, shredding it into countless fragments. Another compelling idea involves the gravitational disruption of a large comet or Kuiper belt object that was captured and torn apart by Saturn's gravity. The resulting debris, initially a chaotic cloud, would have quickly settled into the flat, equatorial disk we see today, ground down into smaller particles through countless collisions over millions of years. This theory of a recent, violent origin elegantly explains the ring's pure water ice composition. They would be made from the icy mantle of that shattered moon and their remarkably low mass. This revelation carries a profound and somewhat bittersweet implication. If the rings are so young, they are also temporary. Cassini data also confirmed that the rings are being slowly eroded away. Micrometeoroid impacts and pressure from sunlight electrically charge tiny ring particles, allowing Saturn's magnetic field to pull them inward in a constant ring rain that drains away tons of material every second. Current estimates suggest they could be completely gone in another 100 million years, a mere blink of an eye in cosmic time. This means we exist in a privileged moment in the solar system's history, a narrow window where a planet as majestic as Saturn is adorned with a jewelry of ice. We are witnessing a spectacular but fleeting show, a masterpiece of destruction that graces our night sky for only a short while before it slowly fades back into the darkness of space. But if you thought storms on Jupiter or the silent shrinking of Mercury were impressive, consider this. Our very own sun is constantly ringing like a gigantic bell, creating a symphony of sound waves so deep and powerful that they literally shape the star itself. This field of study is called heliosismology, and it allows us to perform a kind of cosmic ultrasound, listening in to understand the sun's hidden interior structure in astonishing detail. The process begins with the sun's incredibly violent surface. Convection currents like those in a pot of boiling water but on a monumental scale constantly churn the solar plasma. This ceaseless, turbulent motion generates sound waves that travel inward. These aren't gentle whispers, they are low-frequency pressure waves, true sound, but they would be far too low for human ears to hear. As these waves journey into the sun's interior, they refract, or bend due to changes in temperature and density, eventually being pulled back to the surface by gravity. This continuous inward and outward journey creates standing waves, patterns of vibration that oscillate at very specific frequencies, making the entire sun resonate. Scientists can observe these vibrations by carefully tracking the rhythmic rising and falling of the sun's surface using special instruments on satellites like the Solar and Heliospheric Observatory, or SOHO. By measuring the Doppler shift of light from the solar surface, seeing which parts are moving toward us and which are moving away, they can map millions of these distinct modes of vibration. Each mode, like a different note on a piano, penetrates to a different depth within the sun. By analyzing the precise frequencies of these millions of notes, heliosismologists can reconstruct a detailed picture of the solar interior, much like a musician can understand the construction of a grand piano by listening to the tones it produces. This data has revealed the sun's rotation rate at different depths, the temperature and composition of its inner layers, and even helped locate and understand the conveyor belts of plasma that drive the sunspot cycle. To make this incredible phenomenon tangible, scientists have created sonifications. They take these ultra-low frequency pressure waves and speed them up by a factor of thousands or even tens of thousands, shifting them up into the range of human hearing. The result is not random noise, but a haunting, ethereal chorus of deep booms, hums, and whistles. It is the sound of a star breathing, a direct auditory link to the immense nuclear furnace that sustains all life on Earth. This solar symphony is a constant, powerful reminder that our sun is not a static ball of fire but a dynamic, vibrating entity, and by learning to listen to its music, we can unravel the deepest secrets of its heart. Now, if the sheer violence of a supernova seems difficult to grasp, the end result is perhaps even more mind-bending. The core that remains doesn't just become a ball of super-dense ash. It undergoes a transformation so extreme it defies all earthly logic. The gravitational collapse is so powerful that it literally crushes atoms themselves. The immense force overcomes the repulsion between negatively charged electrons and positively charged protons, forcing them to merge and become neutrons. Essentially, the entire core becomes a single, city-sized atomic nucleus, a vast sea of subatomic particles with virtually no empty space whatsoever. This is a neutron star. To even begin to comprehend the density of such an object, we need a truly staggering analogy. Imagine you could take a single sugar cube, one of those tiny lumps you might drop into your morning coffee. Now imagine that same 1 centimeter cube was made not of sugar, but of neutron star material. On Earth, that innocuous little cube would weigh approximately 1 billion tons. To put that almost incomprehensible number into perspective, 1 billion tons is equivalent to the combined weight of every single human being on the planet, all 7.8 billion of us, condensed into a space the size of a dice. Or, if you prefer a geological scale, it would be like taking the entire mass of Mount Everest, all of its rock and ice, and compressing it down until it could fit inside a standard kitchen teaspoon. This unimaginable density translates to a gravity so potent it warps the very fabric of reality around it. The surface gravity on a neutron star is approximately 100 billion times stronger than the gravity we experience on Earth. If you were to somehow drop a marshmallow onto the surface of a neutron star from a height of just 1 meter, it would impact with the energy of 1,000 hydrogen bombs. The star's magnetic field is equally extreme, trillions of times more powerful than Earth's, enough to strip the information from every credit card on our planet from halfway across the solar system. These stars are not just dead remnants, they are the ultimate laboratories of physics, places where matter exists in states we cannot replicate anywhere else, pushing our understanding of the fundamental laws of the universe to their absolute limit. And as if neutron stars weren't proof enough that the universe has a bizarre sense of humor, it turns out it might also be the ultimate cosmic bartender. Drifting through our galaxy, not far from the supermassive black hole at the Milky Way center, is a vast interstellar cloud known as Sagittarius B2. This giant molecular cloud is a sprawling nursery of gas and dust, but its real claim to fame is its astounding composition. It contains billions and billions of liters of alcohol. Specifically, ethyl alcohol, the very same kind we enjoy in our beers, wines, and spirits. The sheer scale of this intoxicating reservoir is almost impossible to comprehend. Astronomers estimate that Sagittarius B2 holds enough ethyl alcohol to create 400 trillion pints of beer. To put that number into a perspective that completely breaks the human brain, if every single person on Earth drank 1 pint of beer every single day, this cloud could keep the entire planet supplied for several billion years. But before you start designing a spacecraft with a giant straw, there's a very important catch. This cloud isn't a floating ocean of liquid beer in space. It's an incredibly diffuse collection of molecules. The alcohol exists as a vapor spread across light years of space, mixed with all sorts of other molecules and cosmic dust. If you were to fly through it, you wouldn't even get a buzz. You'd simply be in a very cold, very thin gas cloud. The existence of this colossal bar in the sky is far more than just a fun fact. It's a profound clue to the chemical richness of our universe. These complex organic molecules, including not just alcohol but also others like acetic acid, the key component in vinegar, and even simple sugars, are formed on the surfaces of tiny dust grains floating in these cold, dark clouds. Through a process known as surface chemistry, simple atoms like carbon, oxygen, and hydrogen latch onto these microscopic grains. Over millions of years, shielded from harsh radiation, they slowly bump into each other and bond, building up increasingly complex molecules. It's a slow, cosmic-scale chemistry set operating in the void, creating the fundamental building blocks of life in the most unexpected of places. So, is any of this space booze actually drinkable? The short and very firm answer is no, and for a multitude of reasons. Beyond being impossibly diluted, the cloud is also laced with some decidedly unappetizing and downright poisonous chemicals, including hydrogen cyanide and formaldehyde. Furthermore, the alcohol in Sagittarius B2 isn't pure. It exists in 2 mirror image forms, what chemists call enantiomers. The type we enjoy in our drinks is just one of these forms, while the cloud contains a mix of both. Even if we could magically collect and condense it, the resulting mixture would be utterly undrinkable. The true significance of this cloud isn't about potential party fuel. It's about demonstrating that the basic ingredients for organic chemistry, and perhaps even the precursors to life itself, are being manufactured continuously throughout the galaxy, seeding new star systems with the potential for biology long before planets even finish forming. Cheers to that! While our own moon is in a slow, graceful retreat, the story on Mars is far more chaotic and dramatic. The red planet is attended by two bizarre, misshapen moons named Phobos and Deimos, names taken from Greek mythology that mean fear and dread, and looking at them you can start to understand why. These are not the familiar, spherical worlds we might expect. Instead, they are lumpy, cratered, and incredibly small, looking more like giant potatoes than proper moons. Phobos, the larger of the two, is only about 27 kilometers across at its widest point, while Deimos is a mere 15 kilometers. Their surfaces are heavily cratered and dark, resembling the most primitive asteroids found in the outer asteroid belt. This appearance is the biggest clue to their origin. The leading theory among planetary scientists is that Phobos and Deimos are not native to Mars. They are almost certainly captured asteroids, celestial nomads that wandered too close to the planet billions of years ago and were snared by its gravity. Their irregular shapes, low density, and surface composition all strongly support this idea. They share far more in common with the carbon-rich asteroids of the outer belt than they do with any object that would have formed in orbit around a growing planet. The capture mechanism itself is a puzzle, as it's difficult for a planet's gravity to slow a passing asteroid down enough to be captured without it just speeding away again or crashing directly into the surface. One compelling solution suggests that the early Martian atmosphere might have been much thicker, its drag helping to break the incoming asteroids. Another fascinating idea proposes that the two moons could be the remnants of a single, larger asteroid that was shattered by a massive impact either before or during the capture process. But the drama doesn't end with their capture. Phobos, in particular, is living on borrowed time. Unlike our moon, which is slowly spiraling outward, Phobos is doing the exact opposite. It is drifting inward, getting about 1.8 meters closer to Mars every century. This inexorable decline is due to tidal forces, but in a reversal of the Earth-Moon dynamic. Mars rotates more slowly than Phobos orbits, so the gravitational tug from the Moon creates a tidal bulge on Mars that lags behind. This lagging bulge pulls back on Phobos, sapping its orbital energy and causing its spiral of death. In about 30 to 50 million years, Phobos will reach its Roche limit. This is the critical distance where the planet's gravitational pull becomes stronger than the gravitational force holding the Moon together. When that day comes, one of two fates awaits this fearful Moon. If it is still a solid body, the tidal forces will simply tear it apart, fragmenting it into a million pieces. If, as some data suggests, it is already a fragile rubble pile loosely held together by its own meager gravity, it will simply come unglued. Either way, the result will be the same. Phobos will be shredded, transforming from a singular moon into a magnificent, temporary ring system circling Mars. This new ring would initially be dense and bright, perhaps even visible from the Martian surface with the naked eye, a beautiful and haunting memorial to a doomed moon. Over subsequent millions of years, the debris would spread out and slowly rain down upon the Martian equator in a spectacular, endless meteor shower. This impending destruction makes Phobos a unique celestial time capsule. Every close pass to Mars stresses it, creating the distinctive grooves and streaks that line its surface, which are likely the early fractures of its eventual demise. For now, it serves as a stark reminder that even the orbits of moons are not permanent, and that the solar system is a dynamic, ever-changing arena of gravitational forces and cosmic collisions. After exploring the chaotic fate of Martian moons and the cosmic bar hidden in a distant cloud, we arrive at a fact that is surprisingly soothing yet deeply profound. If you were to take every star, every galaxy, every single source of light in the entire observable universe and blend them all together into a single color, what would you get? A brilliant, radiant white, a deep, mysterious blue. The answer, determined by a team of astronomers at Johns Hopkins University, is far more humble. The average color of the universe is a warm, creamy, pale beige. In 2002, after a detailed analysis of over 200,000 galaxies, they officially named this color cosmic latte. The method to find this universal average was both ingenious and meticulous. The researchers didn't simply look at pretty pictures. They used massive spectral surveys like the 2DF Galaxy Redshift Survey. This instrument didn't just capture what galaxies look like to our eyes. It broke their light down into detailed spectra, essentially creating a unique fingerprint for the light emitted by each one. By collecting these spectra from 200,000 galaxies, they could measure the precise intensity of light across every wavelength, from ultraviolet to the far red. The next step was the cosmic averaging. They took this enormous dataset and mathematically combined all this light, effectively calculating a single overall spectrum for the universe. Once they had this master spectrum of all universal starlight, they then translated it into a color visible to the human eye. This process accounts for the specific sensitivities of the 3 types of cones in our retinas, finally revealing the shade that our brains would perceive if we could somehow see the combined light of all things. But why this specific shade of beige? The answer lies in the dominant types of stars and their life cycles. The color is not a static, permanent feature of the cosmos. It is actually changing over time, and it has already undergone a dramatic shift. Billions of years ago, the universe was a much bluer place. This was the era of peak star formation, when massive, brilliant, blue-white stars were being born at a ferocious rate. These stellar behemoths burn incredibly hot and bright, but they are also spectacularly wasteful, exhausting their nuclear fuel in only a few million years before dying in violent supernova explosions. As the universe has aged, the rate of new star formation has slowed. The short-lived blue giants have largely gone supernova, leaving behind longer-lived stars like our Sun, which emit more light in the yellow and green parts of the spectrum, and a growing population of older, cooler red giants and red dwarfs. This gradual demographic shift in the stellar population, from hot blue stars to cooler yellow and red ones, has slowly warmed the universe's overall hue from a cooler blue to the warmer beige we observe today. This cosmic latte is more than just a fun piece of trivia. It is a direct measurement of the universe's evolutionary history, a snapshot of its current stellar constituency. It tells a story of a cosmos that is maturing, settling down, and slowly using up the raw material for new blue stars. The color will continue to evolve. As the remaining blue stars burn out and the countless red dwarfs, which can shine for trillions of years, become the dominant sources of light, the universe's average color will continue to redden. Billions of years from now, the blend may shift to a rosier beige, and eventually, far in the future, to a much deeper, reddish-brown hue as the longest-lived, dimmest red stars become the sole survivors. So the next time you sip a latte, remember you're holding a cup that matches the combined light of every sun in the sky, a quiet echo of the universe's vibrant and ever-fading youth. But just as we find comfort in the universe's average hue, astronomers are chasing a shadow in the outer darkness that could rewrite our solar system's map. For decades, we were taught our solar system had 9 planets until Pluto's reclassification left us with 8. But what if 9 was the right number all along, just not in the way we thought? Mounting evidence suggests a true giant, a hypothetical world we call Planet 9, may be lurking in the frozen expanse far beyond Neptune, its gravitational influence the only clue to its existence. The search for this phantom planet began not with a direct glimpse, but by studying the strange, clustered paths of small icy bodies in the distant Kuiper belt. These objects, known as extreme trans-Neptunian objects, or ETNOS, have incredibly elongated orbits that take them hundreds of astronomical units from the Sun. The peculiar thing is that their orbits are not randomly oriented. Instead, they are grouped together, their closest approaches to the Sun, their perihelia, clustered in a similar direction in space, and their orbits tilted in a similar way. This is statistically very unusual, like several scattered pencils all pointing roughly the same direction. The odds of this happening by chance alone are astronomically low, suggesting something massive is herding them, its gravity sculpting their orbits into this aligned configuration. The leading explanation, proposed by astronomers Konstantin Batygin and Mike Brown, is a planet. Not just any planet, but a super-Earth or a mini-Neptune with a mass roughly 5 to 10 times that of Earth. Its proposed orbit is equally colossal, taking it on a looping path around the Sun that lasts between 10,000 and 20,000 years. At its closest, it might be a mere 200 astronomical units from the Sun, but at its most distant, it could be over 1,200 AU away, making its orbit a breathtakingly long and narrow ellipse. From that distance, the Sun would appear as little more than a particularly bright star, and a single day would last a tiny fraction of its immensely long year. Finding this world is one of modern astronomy's greatest challenges. Its incredible distance means it reflects virtually no sunlight, making it extraordinarily faint, and its slow orbital motion means it doesn't zip across the sky in a way that's easy to detect. The search is on, using the world's most powerful telescopes like Subaru in Hawaii. Astronomers are methodically scanning vast swaths of the sky, looking for that one faint, slow-moving pinprick of light against a backdrop of fixed stars. It's a painstaking process, like finding a single specific grain of sand on a planet-wide beach. The potential discovery of Planet 9 would be a monumental event, not just for adding a new planet to our charts, but for what it tells us about the solar system's violent history. Its existence strongly suggests it was not born in its current distant orbit, but was flung out there during the solar system's chaotic early days when the giant planets jostled for position. This would mean our planetary family's history was far more dynamic and dramatic than we ever knew, with gravitational battles shaping the system we see today. The hunt for this gravitational ghost continues, a thrilling cosmic detective story unfolding in the deepest dark of our own celestial backyard. But if you think the void between stars is truly empty, prepare to have your mind bent by one of quantum physics' most bizarre and beautiful revelations. We often picture space as a perfect, sterile vacuum, an absolute nothingness stretching between celestial bodies, but this couldn't be further from the truth. Even in the deepest, darkest recesses of the cosmos, in the void between galaxies, space is never truly empty. It is a seething, bubbling sea of potentiality, a quantum foam where reality itself is in a constant state of flux. This isn't poetic license, it's a fundamental property of the universe, and it leads to effects we can actually observe. This chaotic underpinning of reality is known as the quantum vacuum. According to the principles of quantum mechanics, empty space is not passive, it is crackling with energy, at unimaginably tiny scales and over incredibly short time periods. Pairs of virtual particles spontaneously blink into existence everywhere all the time. These particle-antiparticle pairs, like an electron and a positron, are born from the borrowed energy of the vacuum itself, mandated by Heisenberg's uncertainty principle. Normally, they exist for only a fleeting moment before they inevitably collide and annihilate each other, returning the borrowed energy to the vacuum and vanishing without a trace. It's a cosmic game of borrow and repay happening too quickly for us to ever directly see, but its consequences are very real. This bizarre process remains hidden from us in most of the universe, the particle pairs appearing and disappearing far too quickly to leave any observable evidence. But place this quantum frenzy at the edge of a black hole, and something extraordinary happens. This is where Stephen Hawking made his revolutionary connection. Imagine a pair of virtual particles popping into existence right at the very boundary of a black hole's event horizon, the point of no return. In a twist of cosmic bad luck, one particle might fall across the horizon, forever lost to the black hole's immense gravity, while its partner is gifted just enough energy to escape, flying off into space as a real particle. From the perspective of an outside observer, the black hole has just emitted a particle. This is Hawking radiation, but there's a cost to conserve energy. The particle that fell in must have had negative energy. This effectively reduces the total mass and energy of the black hole. Over staggering amounts of time, this slow, steady trickle of escaping particles causes the black hole to evaporate. Smaller black holes with stronger tidal forces at their horizons would theoretically evaporate faster and faster until they potentially vanish in a final, energetic burst. For the supermassive black holes at the centers of galaxies, this process is so incredibly slow that they will likely outlast all the stars in the universe, but the principle remains. Even the most voracious monsters in the cosmos are slowly leaking away because of ghostly particles dancing in and out of existence at the edge of reality. This means that the blackest, most absolute darkness we can conceive of is not a void, but a crucible of creation and destruction. The emptiness of space is, in fact, filled with the most profound activity, a quantum symphony playing on an infinite stage, and its faintest echo is the very reason black holes are not eternal. Now, let's shift our gaze from the quantum weirdness of empty space to a completely different kind of cosmic anomaly: stars that aren't really stars at all, and some that are so surprisingly cool you could theoretically reach out and touch them. We're venturing into the strange and elusive realm of brown dwarfs, the failed stars of the universe that blur the line between planet and star in the most fascinating ways. Imagine an object that forms just like a star, collapsing from a vast cloud of gas and dust, but one that simply didn't win the cosmic lottery. It didn't gather enough mass to ignite the sustained nuclear fusion of hydrogen in its core, the defining characteristic of a true star. This is a brown dwarf, sometimes poetically called a failed star. They occupy a puzzling middle ground, too massive to be considered a planet like Jupiter, yet not massive enough to truly shine like our Sun. Their masses typically range from about 13 times that of Jupiter up to around 80 Jupiter masses. Hitting that lower threshold of about 13 Jupiter masses is critical. It's the minimum mass needed to briefly fuse deuterium, a heavy isotope of hydrogen, and a bit later, lithium. But this fusion is a short-lived, sputtering affair, not the long-term hydrogen fusion engine that powers main sequence stars. After burning through their limited deuterium fuel in a mere 100 million years or so, their faint fire goes out and they begin a long, slow cooling process that continues for billions of years. This leads to their most astonishing property, their surface temperature. While newly formed brown dwarfs can be quite hot, many of the older ones that have had ample time to cool down have surface temperatures that are downright comfortable. We've discovered numerous brown dwarfs, like the famous WISE 0855-0714, with surface temperatures right around the freezing point of water, some even as cool as a brisk autumn day, hovering near room temperature. This means that if you could somehow overcome the immense practical challenges of traveling to one and surviving its intense gravity and turbulent atmosphere, you could, in principle, reach out and touch its surface without being vaporized. Of course, there is no solid surface to touch. You'd be plunging into a deep, hot atmosphere of primarily hydrogen and helium, likely filled with swirling clouds of molten iron and silicate dust, a far cry from a hospitable environment, but the temperature itself would not be the immediate cause of your demise. Detecting these faint, cool embers in the vast dark of space is one of the greatest technical challenges in modern astronomy. Because they emit very little visible light, they are practically invisible to optical telescopes. Their peak radiation is in the infrared part of the spectrum, so finding them requires powerful space-based infrared observatories like the Wide Field Infrared Survey Explorer, or WISE, and the James Webb Space Telescope. They are identified by their unique infrared signatures and spectra, which reveal the presence of molecules like methane and water vapor in their atmospheres, molecules that will be instantly torn apart by the intense heat of a true star. This spectral fingerprint is what definitively marks them as ultra-cool, substellar objects. The study of these failed stars is revolutionizing our understanding of the boundaries of planetary and stellar formation, revealing a whole hidden population of dim, cool objects lurking in the galactic neighborhood, often passing by completely unnoticed, the dark, quiet ghosts of stars that never were. And just as we ponder the faint, cool glow of brown dwarfs, our own cosmic home, the Milky Way galaxy holds a secret of its own, a secret shape that defies the classic image of a flat, spinning frisbee of stars. For centuries, we've pictured our galaxy as a relatively flat, symmetrical spiral, but thanks to the revolutionary data from the European Space Agency's Gaia mission, we now know that the Milky Way is profoundly bent and warped, twisting through space like a gigantic, slow-motion S. This incredible discovery was made possible by Gaia's unprecedented precision. Since its launch in 2013, this space observatory has been on a monumental quest to map the positions, distances, and motions of over 1 billion stars in our galaxy with astounding accuracy. It's essentially creating the most detailed, three-dimensional map of the Milky Way ever attempted. By analyzing the precise locations of over 1 billion stars, particularly the bright, young pulsating stars known as Cepheid variables and countless other stellar markers, astronomers were able to plot the true structure of the galactic disk far beyond our own local neighborhood. What they found was a pronounced and asymmetric warp, a twisting of the outer disk that begins to twist in one direction and then curves back the other way, giving the entire structure a distinct, lopsided S-shape when viewed from the side. This isn't a static bend either. The entire warp is precessing or slowly wobbling around the galactic center, completing a full rotation about once every 600 to 700 million years. So what massive force could possibly twist an entire galaxy containing hundreds of billions of stars? The prime suspect is an ongoing gravitational tug of war with our smaller satellite galaxies, most notably the Large and Small Magellanic Clouds. These two dwarf galaxies are currently orbiting the Milky Way, and as they do, their combined gravitational pull exerts a torque on the vast reservoir of dark matter that is believed to form a huge halo around our galaxy. It is this invisible dark matter halo that acts as the intermediary. The gravity of the satellite galaxies tugs on the dark matter, which in turn pulls on the outer regions of the Milky Way's visible disk of stars and gas, twisting it into its current warped configuration. Think of it like placing a small but heavy weight on a trampoline. The fabric distorts and bends not just directly under the weight, but in a wider, more complex pattern around it. The Magellanic Clouds are that weight, and the dark matter halo is the fabric of the trampoline, with our galaxy's disk being warped as a result. This warp is a dynamic and evolving feature, not a fossil from a long-ago collision. The speed and direction of the warp's precession align remarkably well with the predicted gravitational influence of the Magellanic Clouds, providing strong supporting evidence for this theory. It serves as a powerful, visible reminder that galaxies are not isolated, static islands in the universe. They are dynamic, living structures, constantly interacting with and being shaped by their companions, even smaller ones, through the invisible but irresistible force of gravity. Our classic textbook image of a flat, pristine spiral has been replaced by something far more interesting, a galaxy that is gracefully, but decidedly, bent out of shape. Forget the idea that Earth is a lone oasis in a dry solar system. The truth is, water is absolutely everywhere we look. It is one of the most abundant and widely distributed substances in our cosmic neighborhood, turning our previous understanding of a parched universe completely on its head. Let's start with our own moon. For generations, we believed it to be a bone-dry, desolate rock, but advanced orbital reconnaissance has revealed the lunar poles are hiding a treasure trove. Permanently shadowed craters, places where sunlight has not reached for billions of years, trap water ice in their frigid depths. The same is true for Mercury. Despite its searing 400 degrees Celsius dayside, its poles also host these permanent shadows, and radar signals and neutron spectrometer data confirm the presence of significant deposits of water ice, a stunning paradox for the closest planet to the Sun. Mars tells an even more compelling story of water, both past and present. The surface of the red planet is scarred with the unmistakable signs of a wet history: dried up river deltas, ancient lakebeds, and deep canyons carved by colossal floods. But the water didn't just vanish into thin air. A substantial amount of it is still there, locked away as ice. Vast glaciers lie just beneath the dusty surface at mid-latitudes, and the planet's north pole is crowned with a massive permanent cap of water ice. Recent discoveries even suggest the possibility of briny, liquid water lakes lurking deep under the southern polar ice cap, though this remains a topic of active debate. Mars isn't just a dry desert, it's a cold desert with a hidden, frozen heart. But the real game changers, the places that have planetary scientists utterly fascinated, are the icy moons of the outer solar system. Jupiter's moon, Europa, is the prime candidate. Observations from spacecraft like Galileo show a world encased in a smooth, cracked shell of ice, likely covering a global saltwater ocean containing more than twice the volume of all Earth's oceans combined. The heat needed to keep this massive subterranean sea liquid isn't from the distant sun, but from the tremendous tidal forces exerted by Jupiter's gravity. As the moon orbits, Jupiter's gravitational pull flexes and squeezes its interior, generating enough friction heat to melt ice into water, creating a potentially habitable environment despite being over 700 million kilometers from the sun. Then there's Saturn's small, brilliant moon Enceladus, which put on one of the most spectacular shows in the solar system. The Cassini spacecraft didn't just infer an ocean there. It flew directly through massive geysers erupting from a subsurface ocean near the South Pole, analyzing their composition in real time. These plumes, shooting hundreds of kilometers into space, are filled with water vapor, ice particles, and most importantly, a cocktail of organic molecules and salts. This confirmed that Enceladus has a global liquid water ocean in contact with a rocky core, a scenario that provides all the key ingredients for life as we know it: liquid water, a source of energy from hydrothermal vents, and the necessary chemical building blocks. The implications of this universal water are nothing short of revolutionary. Where there is liquid water, there is the potential for life. This shifts the astrobiological search for life beyond Earth from a question of if to a question of where and when. We are no longer looking for a second Earth around a distant star. We are looking in our own celestial backyard at these dark, subsurface oceans where life could have arisen independently. This new understanding is the driving force behind a new generation of robotic explorers. NASA Europa Clipper mission, scheduled to launch soon, is designed to conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, mapping its chemistry and geology to assess its habitability. Concepts are being developed for probes that could land on these frozen worlds, potentially using heated drills or even robotic submarines to eventually melt through the ice and directly explore the alien seas below. The solar system, once thought to be mostly barren, is now revealed as a network of potential aquatic worlds, each holding the possibility of answering the most profound question we can ask: are we alone in the universe? Now, if all this talk of warped galaxies and cosmic oceans makes your head spin, just wait, because according to Einstein, time itself is spinning a different tale for all of us depending on where we are in the universe. This isn't science fiction. It's a fundamental prediction of Einstein's theory of general relativity called gravitational time dilation, and it means that time doesn't tick at one universal rate. It actually passes slower the deeper you are in a gravitational field. The stronger the gravity, the more time slows down. This might sound like an abstract concept from a physics textbook, but its effects are so real and measurable that we have to account for it every single day just to use our phones for navigation. Think of it this way: gravity doesn't just pull on objects, it pulls on space-time itself, stretching and warping it. Imagine time flowing like a river. Near a massive object like a planet, the river of time flows more slowly, like it's moving through thick mud. Out in deep space, far from any large gravitational source, the river flows freely and quickly. This means a clock on the surface of the Earth will run ever so slightly slower than a clock on a mountaintop, and significantly slower than a clock on a satellite in orbit. The difference is tiny, mere fractions of a second over years, but with ultra-precise atomic clocks, we can measure it easily. The most famous and relatable way to understand this is the twin paradox thought experiment. Imagine two identical twins. One stays here on Earth living a normal life, while the other twin blasts off on a rocket and spends years traveling through space at a significant fraction of the speed of light. According to Einstein's theory of relativity, which combines both gravitational time dilation and the effects of high speed, when the spacefaring twin returns to Earth, they would be younger than their sibling who stayed behind. Their clocks literally experienced less time. While we don't have the technology for such a dramatic human experiment, we have tested this with atomic clocks on airplanes. In one famous experiment, scientists flew precise atomic clocks on commercial jets around the world. When they compared them to identical clocks that remained on the ground, the flying clocks were indeed ahead by a few billionths of a second, having experienced a sliver of time less than their Earth-bound counterparts. But you don't need a supersonic jet or a twin to witness this. It's happening right now in your pocket. The Global Positioning System, or GPS, is a network of satellites that provides precise location data to everything from your smartphone to military navigation systems. For it to work, the timing signals broadcast from these satellites must be accurate to within a few billionths of a second. The satellites are about 20,000 kilometers above Earth, in a region where Earth's gravity is measurably weaker. Because of this, the atomic clocks on these satellites actually run faster than clocks on the ground. If we did nothing to correct for this, the GPS signals would become inaccurate by about 10 kilometers per day, rendering the entire system useless within minutes. So, the engineers who designed the system had to pre-program the satellite's clocks to tick slower before they are even launched, specifically to counteract the effects of gravitational time dilation. Every time you use your phone to find a coffee shop or get driving directions, you are passively relying on Einstein's theory of relativity to adjust the flow of time itself. It's a silent, constant correction for the warping of space-time, an everyday miracle of modern physics that keeps us from getting lost. While the solar system holds countless wonders, the title for the single largest volcano anywhere in our celestial neighborhood goes not to Earth, but to our rusty red neighbor, Mars. Behold Olympus Mons, a shield volcano so staggeringly enormous that it fundamentally redefines our concept of a mountain. To grasp its scale, picture the entire chain of the Hawaiian Islands. Now imagine a single mountain that could cover all of it. That's Olympus Mons. Its base is so wide it would blanket the entire state of Arizona, and from that base it rises to a breathtaking height of nearly 22 kilometers, making it almost 2.5 times taller than Mount Everest. If you were standing on its summit, you wouldn't just be in the clouds, you'd be looking down through the majority of Earth's atmosphere, your feet planted on a peak reaching into the vacuum of space. So how did Mars manage to build such an incomprehensible geological giant? The secret lies in a key difference between the two planets, the absence of plate tectonics on Mars. Here on Earth, our planet's crust is broken into a jigsaw puzzle of tectonic plates that are constantly, slowly shifting over the molten mantle below. This movement creates a crucial limitation for our volcanoes. Take Mauna Loa in Hawaii, the largest volcano on Earth. It sits over a stationary hotspot, a plume of superheated magma rising from the mantle. As the Pacific Plate slowly drifts over this hotspot, it creates a chain of volcanoes, each one active for a while before the plate movement carries it away from the magma source and a new volcano begins to form. This process spreads the volcanic activity out over time and space, preventing any single volcano from growing to a monstrous size. Mars, however, is a one-plate planet. Its crust is a single, static shell. Billions of years ago, when the planet was far more volcanically active, a massive magma plume forced its way to the surface and just stayed there. With no tectonic plate moving away, the volcano had an uninterrupted supply of magma for possibly hundreds of millions of years. Lava flow after lava flow quietly erupted, piling up layer upon layer, all in the exact same location. This allowed Olympus Mons to just keep growing and growing, its vast weight slowly sinking into the Martian crust to form a massive depression around its base, further accentuating its unbelievable height. Its slopes are incredibly gentle, typically only a 5% grade, meaning climbing it would be a long, gradual trek rather than a steep ascent, but a trek across a landscape the size of a small country. Comparing Olympus Mons to its terrestrial counterparts is an exercise in sheer awe. The entire Hawaiian Emperor Seamount chain, the most massive volcanic feature on Earth, was built over the same basic process, a stationary hotspot, but it's distributed across thousands of miles of ocean floor and dozens of separate volcanoes because of our mobile crust. Olympus Mons represents what could happen if that entire process was focused on one spot for eons. It stands not just as a monument to Martian geology, but as a silent testament to a different planetary evolutionary path, a world where the geological brakes were off, allowing a single wonder to achieve a scale we simply cannot replicate on our own dynamic, shifting Earth. While we marvel at the colossal scale of volcanoes on other worlds, it's easy to assume every planet has a star to call home, a sun to warm its surface and define its year. But the universe loves to defy our expectations, and some of its most mysterious travelers have no home at all. Drifting through the cold, empty vastness between stars are rogue planets, entire worlds that have been violently ejected from their birth systems and now wander the galactic darkness alone, untethered to any sun. The story of how a planet becomes an orphan is a dramatic tale of gravitational chaos. Most planets form in the relatively stable, spinning disks of gas and dust around young stars. In these crowded nurseries, it's a celestial free-for-all. As large planetary embryos and gas giants jockey for position, their powerful gravitational fields interact, sometimes in extremely unstable ways. A close encounter between two massive planets can be catastrophic. One world might gravitationally slingshot the other, flinging it out of the star's influence entirely at tremendous speed, like a stone from a sling. In other cases, if the planetary system is passing near another star, the foreign star's gravity can disrupt the delicate balance, plucking a planet from its orbit and sending it careening into interstellar space. These events are not rare anomalies. Computer simulations suggest that a single young system can eject a significant number of its forming planets, meaning there could be billions or even trillions of these nomadic worlds adrift in our galaxy alone, far outnumbering the stars themselves. Finding these dark, isolated objects presents an incredible challenge for astronomers. Without a star to illuminate them, they are virtually invisible. Their primary signature is not reflected light, but the faint, lingering heat from their formation billions of years ago, which makes them glow dimly in the infrared part of the spectrum. To detect this faint warmth, we need the most powerful infrared telescopes like the James Webb Space Telescope. The most successful method so far has been a technique called gravitational microlensing. When a rogue planet drifts precisely between Earth and a distant background star, its gravity acts as a tiny lens, bending and briefly magnifying the star's light. This creates a characteristic telltale spike in the background star's brightness that can last from a few hours to a couple of days. By analyzing the specifics of this light curve, astronomers can deduce the mass of the object causing the lensing, confirming the presence of a planet-sized body wandering alone in the void. Each microlensing event is a tiny, fleeting clue in the immense dark, a momentary signal that a lonely world has just passed by. The most haunting question about these wanderers is whether they could harbor life. The immediate picture seems hopelessly bleak. A rogue planet far from any star would be a permanent frozen night, with surface temperatures plunging to hundreds of degrees below zero. Any atmosphere would likely freeze solid and collapse onto the surface in a perpetual icy snowfall. But life is tenacious, and scientists have proposed a fascinating alternative scenario. If a rogue planet were a gas giant like Jupiter, it could potentially host rocky moons with thick ice shells. And just as with Europa or Enceladus, the key could be internal heat. The decay of radioactive elements in the planet's core, combined with the immense tidal forces exerted by the planet on its moons, could provide enough energy to maintain vast, dark subsurface oceans of liquid water beneath the moon's icy crust. In such a hidden sea, sealed off from the frozen surface and warmed from within, the ingredients for life could potentially persist for billions of years. A biosphere on such a world would be completely isolated, thriving in absolute darkness, unaware of a universe outside its icy ceiling, a lone spark of biology in the endless interstellar night. Just as our own planet rumbles with the shifting of tectonic plates, our seemingly silent moon also has its own seismic personality, a reality uncovered by the incredibly sensitive instruments left behind by the Apollo astronauts. Between 1969 and 1972, they placed 4 seismometers on the lunar surface, which together recorded over 13,000 moonquakes before being switched off in 1977. This data revealed a world that is far from geologically dead, but one that shakes in ways both familiar and utterly alien. Scientists categorized these tremors into 4 distinct types, each telling a different story about the moon's inner workings. The most frequent and numerous were the deep moonquakes, occurring about 700 kilometers below the surface. These were relatively mild, rarely exceeding a magnitude of 2 on the Richter scale, and they showed a fascinating regularity. They were triggered by the tidal pull of Earth's gravity, much like our oceans are pulled to create tides. As the moon flexes under this gravitational stress, its interior grinds and fractures, causing these predictable tremors. They would occur in monthly cycles, often clustering around the time when the moon was at its closest and farthest points from Earth in its orbit, providing a rhythmic heartbeat directly linked to its gravitational dance with our planet. A second, more dramatic type were the shallow moonquakes. These were far less frequent but immensely more powerful, with some registering up to a magnitude of 5.5. While that might not sound extreme compared to major earthquakes, on the moon where the ground is brittle and seismic energy travels much more efficiently due to the lack of water to dampen the vibrations. Such a quake would feel tremendously violent and could last for astonishingly long periods, sometimes up to 10 minutes. The cause of these powerful, unpredictable events remains a mystery, though theories point to the slow, global contraction of the moon as its interior cools, causing the crust to slip along fault lines and fracture. The third category were the thermal moonquakes. These were tiny, daily events caused by the extreme temperature swings on the lunar surface. As the sun rises after the 2-week-long lunar night, the surface temperature soars from a frigid -173 degrees Celsius to a scorching 127 degrees Celsius. This incredible thermal expansion causes the cold, brittle crust to crack and pop like an overheated pavement, creating a predictable chorus of small seismic pops every lunar morning. Finally, and most famously, were the quakes caused by direct impacts meteoroids striking the surface. The seismometers were so sensitive they could detect the vibration from a strike as far as 1,000 kilometers away, recording everything from tiny pebbles to larger boulders slamming into the regolith. This data was invaluable, helping scientists calculate the rate of bombardment the moon experiences, which in turn tells us about the past and present impact history of the entire Earth-Moon system. Collectively, these moonquakes have allowed scientists to perform a kind of ultrasound on the moon, mapping its internal structure with surprising detail. The data suggests the moon has a layered interior much like Earth, with a crust, a mantle, and likely a small, partially molten core. The seismic waves travel differently than they do on Earth, indicating a dry, rigid, and fractured interior structure. Understanding these lunar tremors is absolutely critical for our future there. Before we can build permanent bases, we need to know if the ground itself is stable. Could a powerful shallow moonquake damage a habitat? Could the constant rumbling from deep quakes and impacts weaken structures over time? The answers lie in the data from those Apollo instruments, a legacy of discovery that is still guiding our path back to the moon and beyond. Now, if you've ever wondered what it might be like to take a deep breath just outside the airlock, astronauts have a surprising answer for you. After spacewalks, upon removing their helmets back inside the spacecraft, they consistently report a very distinct and unexpected odor clinging to their suits and equipment. The smell of space isn't some ethereal, indescribable scent. It's been likened to a variety of familiar, if bizarre, things. Most commonly, they describe it as a combination of seared steak, hot metal, and welding fumes. Some have even noted a distinct metallic tang, like the smell of ozone after a thunderstorm, or the scent of gunpowder after fireworks have gone off. It's a smell that seems to scream high-energy reactions, a fragrance of the void that is both industrial and oddly organic. So where does this strange aroma come from? The vacuum of space itself is, of course, almost a perfect nothingness, so it can't actually carry a scent to our noses. The smell is created when the particles that do exist out there adhere to the surfaces of spacesuits, tools, and airlock interiors during a spacewalk. When the astronauts repressurize the module and remove their gear, these particles are released, mixing with the cabin's oxygenated air to create the recognizable smell. The leading scientific theory points to polycyclic aromatic hydrocarbons. These are complex molecules that are formed in the intense heat of dying stars and are then scattered throughout the interstellar medium. When these particles settle on a suit, they carry with them the essence of stellar furnaces. Furthermore, the high-energy, ionizing radiation that floods space can break down bonds in materials, a process that can also release volatile compounds that contribute to the scent. There's also a strong likelihood that the distinct odor is partly the smell of ozone. The relentless bombardment of solar ultraviolet radiation can split oxygen molecules, and when single oxygen atoms recombine, they can form ozone, which has that sharp, metallic, electric smell. This creates a wonderfully humorous contradiction. The vast, cold, and silent emptiness of space, the most sterile and inhospitable environment imaginable, apparently leaves you smelling like you've just spent the afternoon in a busy machine shop or working the grill at a barbecue. It's a sensory experience that connects the unimaginable scale of cosmic death and creation to something incredibly mundane and familiar here on Earth. This quirky fact is a perfect reminder that for all its grandeur and mystery, the universe is made of the same stuff we are, and sometimes it even smells like dinner. And just as we contemplate the lingering scent of cosmic barbecue, Saturn presents us with a shape so geometrically perfect it seems to defy the very nature of chaotic weather, a massive, stable hexagon encircling its north pole. This isn't a trick of shadow or light. It's a six-sided jet stream, a roaring river of air wider than two Earths placed side by side, whipping around the planet at over 320 kilometers per hour. Discovered by the Voyager flybys in the 1980s and later studied in stunning detail by the Cassini spacecraft, this atmospheric polygon has persisted for decades, possibly centuries, a mesmerizing and baffling feature with no true equal anywhere else in our solar system. The raw statistics of this feature are enough to inspire awe. Each of the hexagon's 6 sides is about 13,800 kilometers long, longer than the diameter of our entire planet. The structure itself rotates with a period of about 10 hours, 39 minutes, which appears to be the rotation period of Saturn's deep interior, suggesting this colossal weather pattern is locked to the planet's core rotation. Inside its sharply defined walls, the weather is surprisingly calm, like the eye of a hurricane, while the jet stream itself acts as a towering, vertical wall of swirling atmosphere, believed to extend hundreds of kilometers down into the planet. So how does a chaotic, turbulent atmosphere spontaneously generate and maintain such a precise geometric shape? The leading theory points to a phenomenon involving atmospheric waves and shear. Imagine different layers of Saturn's atmosphere rotating at slightly different speeds. Where these layers shear past one another, it can generate instabilities that create standing waves, much like how a swift-flowing river can create stable, stationary patterns of waves around a rock. On Saturn, the immense scale and specific conditions of its atmosphere, a deep, thick layer of gases with no solid surface to disrupt the flow, might allow a particular type of wave called a Rossby wave to become trapped at the North Pole. The mathematics of these waves can naturally produce polygonal shapes, and under the right conditions on a rapidly rotating planet, a hexagon can be the most stable configuration. It's essentially a self-organizing pattern, a persistent atmospheric echo that has found equilibrium in the polar whirlwind. The Cassini spacecraft provided our most breathtaking views of this wonder, using its various filters to peer through the hazes. In visible light, the hexagon often appeared as a pale, yellowish feature, but when viewed in infrared wavelengths that revealed deeper cloud structures, the true complexity emerged. The interior of the hexagon is a dynamic cauldron of its own, with smaller vortices spinning and dancing, some of them large enough to swallow a sizable chunk of Earth. The most captivating views showed the entire region during Saturn's North Pole summer, when it was bathed in continuous sunlight, revealing the hexagon acting as a barrier, containing a completely different weather system within its walls, with a massive hurricane fixed directly over the pole itself. It is a storm within a storm, a geometric frame holding a chaotic masterpiece. This stable, geometric storm challenges our fundamental understanding of fluid dynamics and planetary atmospheres. While we can create smaller, transient polygons in laboratory experiments with spinning fluids, nothing in nature on Earth comes close to the scale, stability, and perfection of Saturn's hexagon. It stands as a stunning example of how the universe can produce order from chaos, a mathematical painting brushed onto the clouds of a gas giant by the invisible laws of physics, a celestial landmark that continues to mystify and enchant all who see it. Just when we think we have a handle on the grand story of the cosmos, it throws us a curveball that rewrites the entire final chapter. For most of the 20th century, the prevailing belief was that the universe, born in the Big Bang, had been expanding ever since, but that this expansion was gradually slowing down. The collective gravitational pull of all the matter in the cosmos, the galaxies, the stars, the dark matter, was thought to be acting like a cosmic brake, gently pulling on everything and steadily decreasing the rate of that expansion. The ultimate fate of the universe hinged on a simple question: was there enough matter for gravity to eventually halt the expansion and pull everything back together in a big crunch? Or would the expansion just continue to slow forever, coasting toward a frozen, dark eternity? In the late 1990s, 2 independent teams of astronomers set out to measure this deceleration by using a specific kind of stellar explosion as a cosmic yardstick. They were observing Type 1, a supernova, which are incredibly valuable because they all explode with nearly the same intrinsic brightness. This makes them standard candles. By measuring how bright they appear to us here on Earth, astronomers can calculate their precise distance. Furthermore, by analyzing the light from these supernovae, they can determine how much the universe has stretched since the explosion happened, which tells us how fast the universe was expanding at that point in the past. The plan was to compare supernovae in relatively nearby galaxies to those in extremely distant ones, looking back billions of years to see how much the expansion had slowed over time. The results were not just surprising, they were mind-shattering. The data from both teams pointed to the same astonishing conclusion. The expansion of the universe was not slowing down at all. It was speeding up. The distant supernovae were much fainter than they should have been if the universe had been expanding at a constant or decelerating rate. This meant that billions of years ago, the universe was actually expanding more slowly than it is today. Something was overpowering the pull of gravity, pushing galaxies apart at an ever-increasing rate. This discovery was so revolutionary and counterintuitive that the teams spent years checking and rechecking their work for errors, but the evidence was undeniable. In 2011, Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics for this discovery, which fundamentally altered our understanding of cosmic evolution. The mysterious force behind this acceleration was dubbed dark energy. We cannot see it, we cannot detect it directly, but we can observe its profound effect on the entire universe. Think of it as the opposite of gravity. While gravity pulls matter together, dark energy appears to be a property of space itself that causes it to push outward. The leading explanation, first proposed by Albert Einstein himself and then discarded, is the cosmological constant, a repulsive energy inherent to the vacuum of space. As the universe expands and more space comes into existence, more of this repulsive energy is created, leading to a feedback loop that causes the expansion to accelerate faster and faster. This discovery paints a startlingly bleak and lonely ultimate fate for the cosmos, often called the Big Freeze or heat death. If dark energy continues to dominate, the acceleration will continue unchecked. Distant galaxies will eventually be pushed away so fast that their light can no longer reach us, causing them to vanish from our observable universe. The cosmos will become a vast, expanding emptiness where galaxies are isolated islands, forever receding from one another. Star formation will cease as gas clouds are pulled apart, existing stars will burn out, and the universe will gradually cool toward absolute zero, a dark, cold, and empty void where the final chapter of history is written in perpetual, silent expansion. But the sheer violence of these winds is only half the story. The true horror lies in what they are carrying. The atmosphere of HD 189733b is not made of benign gases like nitrogen or oxygen. Spectroscopic analysis has revealed it is a hazy, deep blue world, a color that comes not from oceans but from a high-altitude mist containing silicate particles. These are tiny droplets of silicon and oxygen, the fundamental ingredients of sand, and when heated to extreme temperatures, glass. On the day side of the planet, where temperatures soar to a broiling 900 degrees Celsius, these silicate particles are heated into a vapor. Powerful updrafts then carry this vapor high into the atmosphere, where the fierce winds we talked about blast it across the terminator line to the planet's night side. Here, in the relative cold of the night, which is still a scorching 500 degrees Celsius, the silicate vapor undergoes a terrifying transformation. It rapidly cools and condenses back into a liquid form, forming droplets of molten glass, but there is no gentle descent. The relentless, supersonic winds whip these droplets horizontally, creating a perpetual, sideways shooting storm of razor-sharp, superheated glass. This is not a rain that falls, it is a rain that scourges, a sandblasting of the entire planet with liquid-sharp projectiles moving at thousands of miles per hour. The effect would be utterly apocalyptic. Any hypothetical structure or complex molecule would be instantly flayed and eroded into nothingness. To try and comprehend this from a human perspective, imagine the most violent storm you've ever seen or heard about on Earth. Now replace the raindrops with blobs of molten glass and then turn the wind up to 7,000 kilometers per hour. The sound alone would be a continuous, deafening shriek, a sonic boom from countless tiny particles tearing through the atmosphere. The visual would be equally terrifying, a deep blue sky streaked with hypervelocity, incandescent lines of orange and white, a beautiful and deadly aurora of pure destruction. This world makes the most extreme environments in our solar system look tranquil by comparison. It is a permanent, global tempest of unimaginable fury, a stark reminder that the universe is not just a place of wonder, but also one of unimaginable, brutal extremes. But even with the spectacular rings a distant planet like Saturn might boast, you might be surprised to learn that our own Earth has a set of hidden, ethereal companions that are only now coming into focus. Beyond the familiar sight of our brilliant moon, our planet is also attended by a pair of incredibly faint and elusive dust clouds, known as the Kordylewski clouds, orbiting silently in the gravitational sweet spots of space. These vast, diffuse collections of particles are considered quasi-satellites, and for decades after their initial prediction, their existence was hotly debated because they are so tenuous they border on the invisible. These mysterious clouds reside at two of Earth's Lagrange points, specifically the L4 and L5 points. A Lagrange point is a unique position in space where the gravitational pull of two large bodies, in this case Earth and the Moon, precisely balances the centripetal force required for a small object to move with them. This creates a gravitational valley where matter can accumulate and remain relatively stable. The L4 and L5 points lead and follow the Moon in its orbit by 60 degrees, forming 2 points of an equilateral triangle with Earth and the Moon at the other vertices. It was at these theoretical parking spots that Polish astronomer Kazimierz Kordylewski went looking for solid bodies in 1961. Instead of finding a traditional moon, he thought he glimpsed something far more subtle. Two faint patches of light which he believed were clouds of dust. For years, the scientific community remained skeptical, as these clouds were at the very limit of detection, and no one could consistently confirm his observations. The reason these clouds are so devilishly hard to spot is that they are not solid objects reflecting light brightly. They are composed of incredibly fine dust particles, likely micron-sized, which is thinner than a human hair. These particles are thought to be mostly interplanetary dust that has been captured by Earth's gravity and trapped in the stable Lagrange points, but they could also include debris from ancient asteroid impacts on the Moon, slowly migrating to these gravitational eddies. Because the particles are so small and spread over an area nearly 45,000 by 30,000 kilometers across, larger than the full moon in our sky, they don't reflect much light. Instead, they mostly scatter it, creating a glow so faint that it is easily washed out by the glare of zodiacal light, starlight, and even the artificial glow of light pollution from Earth. For decades, every attempted observation was inconclusive, leaving the Kordylewski clouds in a state of scientific limbo. Their existence was finally confirmed in 2018 by a team of Hungarian astronomers and physicists. They didn't just use better cameras, they used a sophisticated polarizing filter system attached to a telescope. This was the key breakthrough. Light from stars and the zodiacal light is not strongly polarized, but light scattered by dust particles can be. By meticulously measuring the angle and pattern of polarized light at the L5 point, the team was able to isolate the specific signature of the dust cloud, distinctly separating its faint glow from the background sky glow. Their images revealed exactly what Kordylewski had described decades earlier, a patch of polarized light consistent with a cloud of dust particles. This confirmation was a monumental achievement in observational astronomy, proving that these ghostly structures are indeed real. This discovery transforms our understanding of Earth's immediate cosmic environment. We don't just have one moon, we have these massive, ephemeral dust moons that are continuously changing shape, losing and gaining particles as the solar wind and the gravity of other planets gently perturb them. They are not permanent structures, but rather dynamic and transient features, likely lasting for only decades or centuries before dissipating and reforming again. Their presence also has practical implications for the future of space exploration. Lagrange points are proposed as ideal locations for space stations and orbital telescopes because they require minimal fuel to maintain position. Knowing that these points are filled with a haze of fine dust is critical information for planning such missions, as the dust could pose a risk to sensitive equipment and solar panels through microabrasions over time. These faint clouds are a beautiful reminder that even in the space closest to us, there are still wonders to be discovered, not with grand gestures, but with subtle, patient observation. And here's a fact that will change the way you see our solar system's very heart. Ask anyone to pick up a crayon and draw the sun, and they will almost certainly reach for the yellow one. We see it as a golden orb in our sky. Our language is filled with references to yellow suns, and even most illustrations depict it that way. But this is one of the most persistent and universal illusions, a trick played on us by our own planet. The truth is, the sun is not yellow. It is, by every scientific definition, pure white. The reason for this color confusion is our life-giving atmosphere. Earth's air is not perfectly clear. It's a sea of nitrogen and oxygen molecules that acts like a constant, subtle filter. When sunlight enters our atmosphere, the shorter, bluer wavelengths of light are scattered in all directions by these tiny molecules. This process, known as Rayleigh scattering, is also the reason our sky appears blue during the day. We're seeing that scattered blue light. The sunlight that actually reaches our eyes directly has had some of its blue component removed, shifting its overall color balance toward the warmer, longer wavelengths of yellow and red. This effect is dramatically amplified at sunrise and sunset, when sunlight has to travel through even more atmosphere, creating those deep oranges and brilliant reds we all love. So the sun only appears yellow to us because we are viewing it from the bottom of an oceanic layer of air that filters its true color. The proof of its real color is visible every day. On a clear day, when the sun is high overhead and its light is passing through the least amount of atmosphere, its color is much closer to a blinding, brilliant white. But the true, unfiltered color is unmistakably revealed by looking at sunlight that has been reflected off a surface in space. The moon is the perfect example. When astronauts walked on the lunar surface, the dust around them wasn't some strange gray material. It was a brilliant, reflective white. The famous photographs of the lunar surface show this clearly. The ground, lit solely by direct, unfiltered sunlight, is a stark white with only shadows providing contrast. If the sun were truly yellow, the entire moon would be bathed in a golden hue, and the astronauts' white suits would appear buttery. But they don't. They appear a crisp, clean white because that is the true color of the light illuminating them. This reality has a major impact on space photography and how we process images from missions like the Hubble or James Webb Space Telescopes. Cameras on these telescopes are calibrated to record light as it actually is in the vacuum of space. When they take a picture of a star, including our sun, they capture its full spectrum. The raw data often looks black and white to our eyes because the sensors are measuring light intensity across all wavelengths. To create the spectacular color images we see, scientists assign different colors to represent different elements or to enhance contrast for scientific study. But for a star like our sun, the most accurate representation, the true color image, shows it as a white disk. Even other stars are classified by their color temperature, and our sun sits squarely in the white category. specifically a G-type main sequence star, which emits its peak radiation in the green portion of the spectrum, but our eyes perceive the blend of all its colors as white. This shift in perspective changes everything. It means that the light bathing the International Space Station, the light that reflects off the rings of Saturn, and the light that travels for years to reach a distant exoplanet is the same pure, unfiltered white light. Our yellow sun is a beautiful planetary-specific illusion, a private view enjoyed only by those of us living under the gentle blue sky of Earth. It's a reminder that our perspective is always shaped by our environment, and that sometimes to see the universe as it truly is, we must first leave our world behind. But if you thought a sideways rain of glass was the most extreme weather in the galaxy, wait until you encounter a star that can reach out across thousands of light years and literally rewrite the laws of physics in its vicinity. We've already marveled at the insane density of neutron stars, but some of these stellar corpses undergo a further transformation that makes them the most magnetically powerful objects in the entire universe. These are magnetars, and their existence proves that nature's capacity for violence knows no bounds. A magnetar is essentially a neutron star that won the cosmic Powerball in terms of magnetic field strength. All neutron stars have intense magnetic fields, but a magnetar is in a league of its own. To grasp the scale, consider Earth's magnetic field, which is strong enough to reliably guide a compass needle. A typical refrigerator magnet has a field about 100 times stronger. Now, a neutron star's field is already trillions of times stronger than that fridge magnet. But a magnetar, its magnetic field is another 1,000 times more powerful still, measuring around 1,000 trillion Gauss. If you could somehow bring a magnetar halfway to the moon, its magnetic field would be so powerful it could erase the information from every credit card on Earth. At a distance of 1,000 kilometers, the field would be so intense it wouldn't just pull on the iron in your blood. It would distort the very electron clouds of every atom in your body, effectively tearing you apart at a subatomic level. These unimaginable fields are thought to be the result of a perfect storm during the star's formation. When a massive star goes supernova, its core collapses. If that core is spinning incredibly fast, the turbulent, dynamo-like motion of its superfluid interior can amplify a pre-existing magnetic field to these ludicrous levels, essentially turning the entire star into a gigantic, spinning magnet. They are rare, making up only about 1 in 10 known neutron stars, and their incredible magnetic power is temporary on cosmic timescales, fading away after 10,000 years or so as the star's rotation slows. This means that to witness one is to catch a brief, terrifying glimpse of a celestial monster in its prime. The most dramatic and dangerous event associated with a magnetar is not a flare or an eruption, but a starquake. We're familiar with earthquakes, where the tectonic plates of our planet shift and release energy. On a magnetar, the entire crust is under unimaginable strain from two forces: the intense gravity trying to crush it into an even denser sphere, and the mind-boggling magnetic field trying to rip it apart. This magnetic field is so powerful that it actually twists the star's structure, warping the neutronium crust like putty. Eventually, the stress becomes too much. The crust, which is thought to be 1 billion times stronger than steel, can't take it anymore. It suddenly fractures and slips, rebounding into a new, more stable position. This is a starquake. The energy released in this event is beyond apocalyptic. In a mere millisecond, a single starquake can unleash more energy than our sun will emit in its entire 10 billion-year lifespan. This energy doesn't just ripple through the star as seismic waves. It is channeled directly into the magnetic field, which acts like a colossal antenna, firing off an intense burst of radiation across the entire electromagnetic spectrum. The most common result is a gamma-ray flare, a sudden, blinding flash of the highest energy light in the universe, but on rare occasions they produce something even more extreme, a giant flare. We have detected only a handful of these events, The most famous occurred in 2004 from a magnetar named SGR 1806-20, which was about 50,000 light-years away in the constellation Sagittarius. Despite that immense distance, the flash of gamma rays and X-rays was so powerful that it actually compressed Earth's ionosphere, briefly altering the propagation of long-range radio signals. If this same event had happened within 10 light-years of Earth, and if the beam had been pointed directly at us, it would have severely damaged our planet's ozone layer, potentially triggering a mass extinction event. It's a sobering thought that a single cosmic event, occurring in a fraction of a second on a tiny, city-sized star on the other side of the galaxy, still had enough power to reach out and give our planet a measurable nudge. Magnetars are the ultimate testament to the fact that in the cosmos, true power isn't always about size. Sometimes it's about concentration. And just when we think we understand our place in the cosmic flow, a far greater and more mysterious force reveals itself, pulling our entire galactic neighborhood on a journey into the unknown. Lurking in the depths of space, roughly 250 million light-years away in the direction of the Centaurus constellation, is a gravitational anomaly of such immense power that it is tugging on the Milky Way and thousands of other galaxies. This colossal, invisible source of gravity is known as the Great Attractor, and its true nature remains one of the most profound puzzles in modern cosmology. Our first clues to its existence came not from seeing something, but from mapping how everything in our region of space is moving. For most of astronomical history, we understood the universe's expansion as described by Hubble's law. Galaxies are moving away from us, and the farther away they are, the faster they recede. This is the overall flow of the cosmic expansion, but when scientists began to measure the peculiar velocities of nearby galaxies, that is, their individual motions relative to this overall Hubble flow, they discovered something startling. Our local group of galaxies, which includes the Milky Way and Andromeda, along with our entire Virgo supercluster, are all deviating from the expected path. Instead of moving with the pure expansion of the universe, we are being pulled sideways, hurtling through space at a breathtaking velocity of over 600 kilometers per second toward something we could not see. Pinpointing the source of this pull was the next challenge. By meticulously mapping the motions of tens of thousands of galaxies, astronomers were able to trace the gravitational current back to a specific region of space, a gravitational focal point they named the Great Attractor. The sheer mass required to exert such a pull on millions of galaxies is almost incomprehensible. It would need to be the equivalent of tens of thousands of Milky Ways, a mass concentration on a scale that dwarfs even the largest known galaxy clusters. For a long time, its incredible gravitational influence was the only evidence we had, because looking directly at it presented a nearly insurmountable obstacle. It lies directly behind the plane of our own galaxy, an area astronomers call the zone of avoidance. This zone is not a physical barrier, but an observational one. It refers to the band of the sky that is obscured by the thick disk of the Milky Way. Here, our view of the distant universe is completely blocked by vast clouds of interstellar gas and dust and an overwhelming density of stars. It's like trying to see a distant city through a thick, perpetual fog bank. Visible light and other wavelengths are simply absorbed or scattered, rendering everything behind it effectively invisible. For decades, the Great Attractor remained a ghost, a gravitational signature without a face, its true identity hidden behind this cosmic curtain. The breakthrough began with our ability to see in new ways. While optical telescopes were useless, certain wavelengths of light can penetrate the cosmic fog. Radio telescopes, infrared observatories, and most importantly, X-ray telescopes like NASA Rosat and Japan's Suzoku satellite could peer through the obscuring material. They revealed that the Great Attractor is not a single, unimaginably dense object, but rather the core of a much larger structure known as the Laniakea supercluster, of which our own Virgo supercluster is just a minor appendage. Laniakea, which means immense heaven in Hawaiian, is a cosmic filament containing over 100,000 galaxies. The heart of this vast supercluster, the point toward which we all flow, is a massive galaxy cluster called Norma Cluster, surrounded by other enormous clusters like the Centaurus cluster. This discovery solved part of the mystery. The gravitational pull comes from the combined mass of this dense knot of galaxies, dark matter, and hot gas. However, it also deepened the mystery. The sheer amount of normal, visible matter in these clusters still isn't quite enough to account for the immense pulling force we measure. This strongly suggests that the true engine of the Great Attractor is an even greater concentration of dark matter, the invisible scaffolding of the universe which provides the extra gravitational muscle to tug on us so effectively. Our journey toward it is far more than a curious orbital path. It is a tiny part of the grand, gravity-driven choreography that shapes the universe on the largest scales, as galaxies and galaxy clusters flow along invisible filaments of dark matter toward the densest nodes in the cosmic web. We are caught in a river of space-time, flowing toward a destination we once couldn't see, driven by the hand of darkness itself. And after contemplating the immense gravitational pull of the Great Attractor, we find that our own galaxy holds structures of such colossal scale that they force us to completely rethink our place within it. For centuries, we pictured the Milky Way as a relatively flat disk of stars with a central bulge. But in 2010, astronomers analyzing data from the Fermi Gamma Ray Space Telescope unveiled a discovery that shattered that simple image. Two enormous, symmetrical bubbles of energy erupting from the galactic center, extending tens of thousands of light-years above and below the plane of the disk. These are the Fermi bubbles, and they are nothing short of a monumental eruption frozen in time, a pair of cosmic ghosts hinting at a violent event in our galaxy's past. Visualizing the sheer size of these structures is a challenge for the imagination. Each bubble stretches for 25,000 light-years from the galactic center. That means the entire structure, from the top of the northern bubble to the bottom of the southern one, spans a breathtaking 50,000 light-years. For perspective, our solar system is only about 27,000 light-years from the center, meaning one of these bubbles towers over our entire neighborhood. If our eyes could see in high-energy gamma rays the wavelength in which these bubbles were discovered, the structure would appear to occupy a huge portion of the southern sky, stretching from the constellation Virgo all the way down to Grus the Crane. Their discovery was a classic tale of scientific serendipity. The Fermi telescope was designed to scan the entire sky for gamma rays, the most energetic form of light in the universe. As scientists processed the data, they were trying to filter out the background fog of gamma rays that permeates our galaxy, which comes from cosmic rays interacting with interstellar gas and starlight. Once this diffuse emission was subtracted, two massive and distinct lobes of gamma ray emission emerged, standing out in stark contrast against the darker sky above and below the galactic plane. They had sharp, well-defined edges, almost like an hourglass or the outline of a giant balloon, and they were emanating perfectly symmetrically from the very heart of the Milky Way. It was a structure no one had predicted, a previously invisible part of our galactic architecture suddenly revealed. So what could possibly create such immense, energetic structures? The prime suspect sits right at the source of the bubbles, Sagittarius, a star, the supermassive black hole at the center of our galaxy. While it's relatively quiet today, the presence of the Fermi bubbles is the strongest evidence we have that it was once an incredibly active and violent engine. The leading theory suggests that in the relatively recent past, Sagittarius, a star, went through a period of intense activity, likely consuming a large amount of matter, perhaps a massive gas cloud or even a star. As this material swirled into the black hole's accretion disk, it became superheated, and a tremendous amount of energy was released not just as light, but in the form of powerful jets and outflows of energetic particles. These particle jets, shooting out perpendicular to the galactic disk at nearly the speed of light, would have blown a cavity in the surrounding halo of hot gas, inflating these gigantic bubbles and filling them with fast-moving cosmic rays. As these high-energy particles interact with the thin gas within the bubbles and with light from the galaxy itself, they generate the intense gamma radiation that we now detect. An alternative, though not mutually exclusive, theory points to a frenzy of star formation at the galactic center. The region around Sagittarius, a star, is densely packed with stars, and in the past, a wave of star formation could have led to a chain reaction of supernova explosions. The combined energy from thousands of these stellar explosions going off in a short period could have also blown a powerful wind out of the galaxy, potentially helping to inflate the bubbles. The truth likely involves a combination of these events, a black hole outburst coordinated with a starburst phase, creating a perfect storm of energy that left a permanent scar on the face of our galaxy. The existence of the Fermi bubbles forces a profound shift in how we view the Milky Way. We are not living in a serene, stable spiral galaxy. We are living in the aftermath of a titanic eruption, residing within a cosmic structure that was shaped by a cataclysm so powerful its remnants still loom over us. They are a stunning reminder that even our seemingly quiet galactic center is capable of waking up and unleashing forces that reshape the entire galaxy, a dormant dragon whose past roar we are only now beginning to hear. And so we reach the end of our journey through the cosmos, a tour that has taken us from our own drifting moon to the warped disk of our galaxy, from worlds of diamond to storms of glass. Just think about that for a moment. We've explored a universe where entire planets are kicked out of their solar systems to wander the eternal night, where stars ring like bells and space itself smells of seared steak and welding fumes. We've stood in awe of volcanoes so large they would blanket entire American states, and we've peered into the heart of a storm on Jupiter that has raged for centuries yet is now slowly fading before our eyes. Each one of these facts is a testament to a simple, breathtaking truth. The universe is far stranger, more violent, and more wonderfully bizarre than any lesson plan could ever contain. What's even more incredible is that this is just the beginning. Every single one of these discoveries, from the subsurface ocean on Pluto to the hidden Fermi bubbles towering over our galaxy, was completely unknown just a generation or two ago. They were secrets the cosmos was not yet ready to give up, and that is the most exciting part of all. This is not a finished story. The maps are not complete. For every mystery we've solved, a dozen new, more profound questions have emerged. What dark energy is accelerating the expansion of the entire universe? What does the hypothetical planet 9 look like, and what will its discovery teach us about our solar system's chaotic youth? Could there truly be life swimming in the dark, salty oceans of Europa or Enceladus, completely unaware of the universe above the ice? This endless pursuit of understanding is what makes science so profoundly human. It's a reminder that curiosity is our greatest tool, and that there will always be another horizon, another mystery waiting just beyond the edge of our current knowledge. The classroom gave us the foundation, but the real adventure is just getting started. Now we want to hear from you. With 30 facts to choose from, which one absolutely blew your mind? Was it the terrifying reality of a hypervelocity glass storm on an exoplanet, or the haunting beauty of a dying star's final, diamond-hearted sigh? Did the sheer scale of Olympus Mons reshape your sense of what's possible? Or did Chinese letter weirdness of Hawking radiation and virtual particles leave you questioning the very nature of reality? Let us know in the comments below. We read every single one and love hearing what sparks your sense of wonder. If this journey beyond the textbook has left you hungry for more cosmic mysteries, you're in the right place. We're just getting started. Make sure to hit that subscribe button and ring the notification bell so you don't miss our next adventure into the unknown. Until then, keep looking up. The universe has countless more secrets to share, and we can't wait to explore them with you.